Okay, so hi everyone. So this is the third day of Leetcode problems, and today we're going to be solving a problem which is called as sort stack. It's the problem is, as the name indicates, we just have a stack full of numbers, full of integers. It can be positive or negative, and we have to sort it in the minimum time complexity and space complexity in the most optimal way possible. So the problem statement goes something like this. You just have to write a function that takes in an array of integers representing a stack. It recursively sorts the stack in place. So you have to use recursion and you have to do it in place. These are two conditions, or rather suggestions, to solve this problem, and returns the stack. And for the sake of implementing a stack in Python, we can just use you can just use an array, and we can use a pop method to be able to pop the final element out of the stack, and we can also use an append method to push the element into the stack. These are the only two operations which are allowed as per the question. And we can also peek at the element on top of the stack, so we can see what element is there either by popping or just by accessing that last index. So this is the condition. And the most important thing is you're not allowed to use any other data structures, and your solution must be recursive. So intuitively, if I was allowed to use another data structure, maybe I would pop all the elements of the stack and push it into a list or something, and then perform merge sort or whatever n log n operations is already available to me, which I typically do. But in this case, I'm not allowed to do that. I can't use any other data structure than the one that is provided to me, which is the stack. Okay, so they mentioned that I should do this recursively. Whenever when I come across the term recursion, I know that a recursion internally uses a stack in memory. So whenever you're actually calling another function recursively, it is taking up memory inside the recursive stack, which is part of the compiler itself. So what can I do? What can I do with that information? So if I have an array like this, -5, 2, -2, 4, 3, 1, the only operation that I can do is pop this is look at the element which is 1. So I can pop the last element which is 1, but I don't know what else is there in the array. I don't know if the rest of the array is sorted. For the most part, it will be unsorted. So there is no other way than to pop all of the elements out of the stack and examine each of the element, but I have to keep track of it simultaneously. So that is where recursion comes into place. The algorithm goes something like this. So as soon as I pop an element, for example, I pop 1, then the immediate next element is 3, which is greater than 1. So I can't insert 1, I have to pop 3 as well, because I can only insert 1 if the element which is there in at the top of the stack is lesser than 1. Otherwise I have to call a separate recursive call which will sort the array internally and put it back into the place. So there has to be two recursive calls. One is to pop the element from the stack, and the second recursive call is to sort the remaining elements in the stack and then push it. So that's how we go. Since I don't have like a pen and paper setup, it will be very hard to for the person who's viewing this to visualize. So let me just go right into the coding part, so at least it'll be understandable. Okay, so what should I do? Okay, so there's a function called a sort stack. I know that I'm going to call this function recursively, so I have to write a base case. Whenever you want to write a recursive method, you have to establish a base condition. What is the base condition for this method? When am I going to stop calling sort stack? When only if the stack is empty, right? If len of stack is equal to 0, I'm going to return stack. This is when my recursive call of the sort stack of the parent method stops when there is no stack element, because I know the operation that I'm going to do is pop. So uh, I'm going to access the topmost element of the stack. Okay, I'm going to pop this element, and what can I do after popping? I have to see if no, as soon as I pop the element, I have to make sure that I call the function recursively. Yeah, I'm passing in the new stack where the pop operation has already happened. So in this case, Because of this operation, the function keeps getting called recursively until all of the elements are popped out, and they are stored virtually. They are stored in a recursive stack. So whatever the elements were in the stack, they are now in the recursive stack. So that is what has happened right now. Okay, so once I have that, the next operation that I have to do is insert in the sorted order. Because I have to do it in place, I have to insert all the numbers that I just popped back into the stack that I originally have, but this time I want to make sure they're sorted. So let me just initialize or just call a function insert sorted order or something. Yeah, insert sorted order, and here I need to pass my stack and the value that I have, the latest value that I have. I want to make sure it's inserted properly. Once everything is inserted, just return stack, because I want to make sure that this particular method will return me a stack which will be in the sorted fashion. So that is up to me right now. I want to make sure that this function is responsible enough to do that. Okay, so when I call this sorted this particular, I'll just take as a value, so some sorted element of the stack, I want to make sure that this will insert this value into the stack in a sorted order. How can I do that? How do I know that it will be sorted if I can insert? The only time, so the base case of this particular method is the fact that I'm going to insert it only if the element at the top of the stack lesser is lesser than the current element. Otherwise, I'm not going to insert it. I'm going to keep calling this method until I find something like that. Okay, so there are two conditions. If length of the stack is equal to 0, even then I'll be putting it, because that is more often the case where the base case ends, or if the element at the top, if the value that I have is greater than the element at the top. How can I see the element at the top? I can just peek at the last element. If this is the case, I want to make sure that I append it into the stack. Okay, append it into the stack. So this is done. If that is not the case, if that particular element is not is for example is not in sorted order, I want to pop that as well. So I'm going to take that, I'm going to pop the latest element from the stack. So as soon as I pop the topmost element, I want to call the method again, because yeah, I want to call the method, I want to pass in the same stack, but this time the value, I'm going to pass in the same value, because the top is getting populated again and again, but this value has still not gone into the stack. That was my primary goal of calling this method. So I'm going to pass in the same value until that gets appended at some point or the other. So I'm going to call this, and it will at one point it is going to get appended into the stack, and it is going to do so in the most rightful manner. So after that, I'll have the latest element on the top of the stack. So I'm going to do that. I'm going to make sure that that goes in as well. So, yeah, I'm just going to return the stack. I think this should be enough for this, because we are calling in two recursive methods, and we are inserting it in the sorted order only if we have set up the base case properly, and if this base case is not achieved, this is getting called again with the same value. So until and unless this value gets appended, it keeps calling from whatever is inside the stack. Yeah, so I'm checking that the topmost element is lesser than the value that I have. Okay, so this should work. Okay, yeah. So the time and space complexity of this problem. The time complexity is what are we doing? We are popping all of the elements in the stack, and this method is being called n times. and internally this method is also being called n times, or at max n times. So the worst case complexity is n into n, which is O of n square, and the space complexity is O of n, because I have one stack already, and I am using an extra recursive stack to maintain all of these operations. So it's an O of n square solution with a space complexity of n. I hope it's difficult to visualize this, I know, because it has to be a pen and paper setup to properly understand what goes in and out of the stack at each iteration. But this code works, and this is the perfect algorithm to sort a stack in the most efficient way possible. So I hope you guys understood this problem. Yeah, I don't know if I explained it well enough, but yeah. So thank you. That's it for this problem. Let's meet in the next one. Bye. Good night.